You make it bigger so that you comply with the requirement.
But you said there's no kind of requirements, who's producing the requirements then? If it's
There is. So the turbine manufacturer does a code of practice, DNV code of practice for monopile design. And the turbine manufacturer will tell you, you've got to satisfy these things. You can't have more than this tilt. Because if it tilts more, think of the gearbox, the etc., there can be faster wear and tear of the gear. If it tilts more, the blades may hit the tower. If it tilts more, the cooling fluid inside can't circulate properly. Right? If it tilts more, the mass acts as eccentric way, you get a lot more movement on a foundation. So roughly half a degree is allowed. Till now, but they want to increase it, but it's under discussion. Second point is, another final point is, once you know these characteristics, you can then find out the natural frequency. Okay? Once you do this thing, you know the natural frequency. So what we have done in the class last week was a fixed base cantilever. The formula what you showed me is a fixed base cantilever, what I showed last week. But here, this is not a fixed base, and end there is spring. Yeah? The fixed base, what we did was a problem. Just give you an example of the problem was last week we did a problem which was like this, isn't it? But actually this is mass here, the tower length, tower EI, fixed base. But not a fixed base, but sitting on some springs. It's a bit more complicated to do. Give you solutions, how to do it, and give the Excel sheet that can do this for you. Right? Or you can easily do it in a finite element or any program. Basically what you do, you set it up, the whole geometry, and you find out the eigen solutions of the problem. So those who have done some dynamics can easily recognize that. But once you set the whole problem up, give the pile head mass, you give it the top of mass, and the stiffness, and to the springs, you find out the eigen solutions. They are the natural frequencies. Okay? Now, so each, depending on the foundation stiffness and the tower diameter, wall thickness and length and the top mass, there will be a frequency. The frequency depends on many things. Okay? Frequency basically means, if I take this structure like that and I give a small tap and then see how it decays. So what happens once I take the load off, it will start to happen its own frequency, and the frequency is the natural frequency. What it means, just to show you here, once I give a small perturbation or a small disturbance, that is a load off, it would decay naturally. It's like you take a water and you take a ball and you push it down and see how it bobs. Once you take the load off, it will bob and come to a standstill. So what it will do something like that, right? So basically, once you take the load off, so that will give you the natural frequency, right? If it takes longer time to decay, low damping, faster decay, high damping, depending on this scale. So this is a function of the geometry and the stiffness and the whole thing, right? That is the actual frequency. But that's not the target. Target is that we need to target that frequency. So if it actually is not that one, we change the parameters to meet the target. Is it now clear? There are two terms, target and natural frequency. So natural frequency is the frequency of the whole structure its own. So depending on the foundation stiffness, so means the pile diameter, the soil, the tower length, tower diameter, wall thickness, top mass, you get one frequency. If you change some components, you will again change the frequency. But the target is what you should target. Okay? In terms of loads, the loads on the whole thing are wind load. Wind load will act, and the main thing to find is what the load at the top of the tower. So the thrust on the top of the tower. Because the whole wind will be captured by the blades. The blades will give a point load in the top of the tower. Right? So, to do a very simplified calculations for wind turbines, what you can do, you can then see, let's see that's the foundation level. So that's a hub level. Say 105 meter in the morning, so that's a hub level. So here you get the thrust load coming from the blades, right? That's the wind load. Second is the wave load. The wave will apply there. Say that's my water level. There will be wave acting here. That's the wave load. That's the wind load. That's the wave load. There are the two main loads, big loads, right? This can be 1 to 2 meganewton. So this load is 1 to 2 meganewton of load. This can be 3 to 10. Meganewton of load. The massive load acting, right? Then there are loads due to the rotor. Means if the three blades are not pitched accurately, there can be a load due to the asymmetry. That means, say for example, these three masses are not the same, there is a small difference, that will cause a wobble. That wobble will give you a small load at the top. That is the 1P loading. That's the 1P load here. That load is acting here as well. So this load will be apart from the wind load, and also another one, this 1P loading. But this is in kilonewton range. This is in kilonewton range. Look at this. So we can ignore that in our calculation for moment. For our cases, we can ignore that. Wind and wave is adequate. Meganewton is kilonewton, so quite the noise level. So you can ignore that. There's another load called the blade passing load. That means, think of the tower. Think of this configuration where the blades are not in front. What is the load on the tower? The load is in the full thrust at the tower. Think of a case when the blade comes in front. You only get load up to the middle part, or the small part, isn't it? So you, as soon as the blade passes, you get a drop in the tower load. So a big tower load and a small tower load. That's a 3P load. So that is at somewhere in the tower. That's also in a kilonewton range. So you can ignore that. When you do your calculation, ignore the 3P load as well. That's again in the kilonewton range. That will be, if this is frequency, it will be even more closer, isn't it? That is 3P loading in kilonewton, you can ignore for foundation design. Now, if I want to put everything in one particular diagram, there's a target frequency. What is that? So, if you get a particular site, you want to start the turbine, you want to start the design of whole wind farm. First thing what you will do is, what's the site? The site is the wind site. So wind site will give you a spectrum. That means where are the wind frequencies? That is somewhere very, very close to zero. Right? Very, very so. So if you go on a flight, often you see turbulence, isn't it? We don't see it very often. You only see sometimes, isn't it? As you go higher up in altitude, often see the pilot says there's a turbulence, please put your seat belts on. So you see the turbulence, the whole thing turbulence. That's the wind eddy moves past the thing. That's the very low frequency. That's here. Very, very low frequency. Typically every 100 seconds. So it comes every 100 seconds. So it's not that. So you got to be careful how you at a time, what speed you maintain for the system. The wave is a function of the sea. It is a Chinese sea, or Irish sea, or North Sea, all are different waves. So typically North Sea is a 10-second period. Typically North Sea 10-second period. So here it is 0.1 hertz. So 10 second means 0.1 hertz. If you look in the Chinese sea, in the chapter you will see they are like 4 second, 5 second. So 4 second, 5 second means 0.2 hertz, 1 by 5, 0.2 hertz. For Chinese sea, this will be somewhere here, 0.2. So this is the spectrum. This spectrum means the wave has got a wide frequency. There are not one frequency but many frequencies in a wave. So this shows the maximum wave energy is in this particular frequency. That's called a spectrum. So this spectrum and this wind spectrum and wave spectrum would vary from place to place. It's not same everywhere. Right? Depending on where you are in the globe, where you are in the earth, depends on that. It's all about the location of the particular place. This part, 1P frequency, that is the cut-in rated. This is a function of your choice of turbine. If you put an 8 megawatt turbine, this would be different than a 3 megawatt turbine. So this 1P is for a 3 megawatt turbine. Look at the interval, 8.6 to 18.4 RPM. So this is 8.6. 8.6 means 8.6 by 60 will give you 0.14. And 18.4 is 18.4 by 60 will give you 0.31. So this spectrum is for 3 megawatt turbine. But for 8 megawatt turbine, you have a different spectrum. Yeah? So this is a function of the spectrum of the wind turbine spectrum. Turbine, what you chose, its characteristics. Go to the brochure, find out that cut-in, rated, you get this range. Right? If it is 3-bladed, you get 3P frequencies. How? 0.14 times 3, 0.42. 0.31 times 3, 0.93. That is the 3P. That means this is this big load, small load, that big load, small load. So these are all cyclic loads. I mean they are coming in cyclically, periodically. That is, they are applying some cyclic load, some dynamic load to your flagpole with a massive charge. Yeah? So to your wind turbine, these are the loads applied. Would you dare to put your turbine here in this range? No, why? It will resonate. If it resonates, you will start to wear and tear your gearboxes, your blades will start to crack, you need a higher maintenance cost. In some cases it might fail. because you are trying to resonate, right? So you got to avoid. You got to avoid the whole thing. So that's why your target is not in these bands. If by mistake you are in this band, you got to abandon your design. Nobody will certify your design. It's wrong. Right? So then the natural choice, there are basically three, they name it. Soft means you make it lower than 1p. It may be impossible to make it such a low frequency. So lower than 1p. Lower than 1p is called soft design. You can make it bigger than 3p. That would be even expensive. This is not so possible. The natural design is between this band, in this sort of band. That's